Go ahead.
All right. Thank you.
Given my talk is not necessarily an AI talk, it's good to have it out right now. So I'm talking on, my talk is Heterogeneous Prompt Processing Challenges in DUNE. And I realize I have other DUNE collaborators in the room, so prompt processing in DUNE could actually mean 3 different things. And for the purpose of this talk, it's prompt processing or supernova workflow. But disclaimer, this is not an AI talk. Can you hear me okay? Yeah. This is not an AI talk like the rest of the talks in the session. I originally submitted it as part of the multi-messenger astronomy category. DUNE or we do one messenger, namely neutrinos. But we are robustly using many types of AI in our reconstruction and analysis chains. I am not qualified to speak on the merits or drawbacks of any of them, but I will mention the various implications for our distributed computing and distributed data storage that arise from them, however. Yeah, the first Condor, not yet HT Condor Fermilab was evolved. And actually Fermilab used load leveler 10 years before that, and I will also use that, which load leveler was HT Condor under the covers. My first Condor week was in 2005. I was also at the Open Science Grid ceremony in Milwaukee, Wisconsin as part-time OSG staff at that point. I've been involved for the DUNE collaboration since its formation 2015, and I've been the co-lead of data management for DUNE since 2017. I recently also took on the role of US facilities for DUNE. We've been accruing data all that time from 6 tests being run so far, 42 petabytes on tape. I'm actually quite impressed by my astronomy colleagues who are encoding large chunks of the universe in less space than what we were doing, few number of charged particles, a few number of neutrinos. Most of my previous talks at this conference have either been asking some new exotic feature of HT Condor or showing how the said new feature works so well, but not this time. HT Condor is behaving just fine and expecting to scale all up to full DUNE scale without incident, and thanks to the dozens of team members over the years who helped that happen. So the deep underground neutrino experiment, otherwise known as DUNE, our main purpose is to be a long baseline neutrino experiment. So we start at Fermilab. We make a neutrino beam of muon neutrinos. We have a near detector to detect the initial composition of the beam. And then 1,300 miles away in South Dakota, we'll have a set of far detectors, eventually 4 of them. We'll have 2 to start with. And you can think of this as a long interferometer in which they start as one kind of neutrino, they'll end up as another one by the time due to interference between the various waves of neutrinos. So what do we have in South Dakota right now? This is blurry. I don't know if my eyes are, but anyway, this is the south cavern of surf as it existed 2 weeks ago. I took this picture. 500 feet long, 90 feet tall, 4,850 feet underground, and we have 2 such caverns like this. And our first of 4 modules is going to be built in this cavern. On the front end of this cavern, we're viewing there, you see about 2% of the steel is eventually going to be part of the cryostat. Many, many tons of steel and 10 kilotons, 10 kilometric tons of liquid argon. And the start of science, in other words, when our first detector is full and we're ready for signal, is expected to be in early 2030. The beam will come approximately a year and a half after that. So for the first year and a half or so, we're going to be sitting waiting for astronomical phenomena of various sorts. Even though we've got 10 megawatts of cooling in that cavern, almost all of it is cooling the cryo and the DAQ readout. There's very little remaining power capacity to put computers in the cavern or, for that matter, above ground, because there's really not any space there to build extra buildings on top of the mountain. So your typical neutrino experiment would build an online farm right by their detector, as our current experiment NOVA has done. For doing that, it's not an option. If we're going to process, we have to do it elsewhere than Leeds, South Dakota. So what is the challenge of DUNE? Our volume of data, the data we're going to take in the first 8 years is less than what CMS or Alice have got on tape already. So that's estimating we'll take something like 500 petabytes of data on tape. By that time, we'll need 100,000 current cores of CPU. It will have to be about as big as the CMS Tier 1 is now. So people can build systems that big as far as CPU, as far as disk, as far as tape is concerned. What we're dealing with is a huge event size per event. 50, okay. So this is the so-called horizontal drift detector. You see this vertical assembly going up here, 9 meters tall, top to bottom. These, by the way, were designed by the physical science lab at the University of Wisconsin in the early days. So there's not a lot of channels, but you're reading them out for a fairly long time, in this case, 2.6 milliseconds. So every 500, that adds up very quickly, 3.4 gigabytes per trigger record, presuming that you do not zero suppress. The second one is called the vertical drift detector. It's simpler, but the electric field goes from top to bottom. The drift volume is twice as large, so you have to actually read it out for twice as long for your charged particles get to the top. So with both of these, the issue is this is a huge memory size, and the existing framework that has been used to do neutrino analysis for the last 15 years or so just can't cut it anymore. And we have a lot of very smart people writing a totally new framework to handle the memory management better of large objects in memory. So in theory, you could, and in practice, we will analyze different chunks of the detector separately in different jobs. So our special challenge is supernova burst readouts. Now so far, the only neutrino producing supernova was SN1987A that happened when I was a freshman, or no, rather senior in undergrad. So there's a lot of time-dependent information that can be seen from a supernova. At some points you get neutrinos, at some points you get antineutrinos. And you'd like to get this whole time evolution curve captured on tape, and you could, in theory, learn a lot about supernova thing if you get that. The trap is it does have to be inside the Milky Way galaxy. If it's outside the galaxy, so I've seen in other talks, supernovas happen all the time, but galactic supernovas don't happen all the time. So when we get a supernova burst trigger, we have to read out the full detector, not for 5 milliseconds, but for 100 seconds. 140 terabytes from one of the detectors, 180 from the other one. And then we'll have to split that in thousands of files to get it back to where we're going. And the trigger characteristics are such that we will not get a supernova once a month, but we will get something that looks like a supernova trigger because of background at least once a month, we think. And so it's a unique challenge to move data from SURF to Fermilab or elsewhere and then process it in a timely manner. Just for reference, a beam neutrino will make a track that will go for several meters in the detector. Supernova detectors are a few between 10 to 100 MeV, so they will only go for a few centimeters in the detector, and you'll have maybe 100 of them. But your background to that is you also have radiative beta decays happen, which also have about the same track length. So that's the background. That's why you'll get a lot of false positives. If you want to make your thresholds, you're sure you really get supernova. This also puts huge, very high uptime requirements on DUNE. I believe our number is 97.5% uptime. We got to have the DAQ up and reading. So there are studies currently underway to use AI and ML to improve signal isolation over background, which is radioactive decays. My colleague Mike Wang is doing those. These were a recent demo in the American Science Cloud. My boss Ali Gushki is here in the room. He knows everything in American Science Cloud. Feel free to ask him. He'll be glad to talk to you about that. So The networking is coming. In fact, most of the fiber is already laid to get from South Dakota. We're at the far end of South Dakota up here in the Black Hills, all the way back to Fermilab. Two independent routes going down two different mine shafts. They don't even come up the same road. There's no thing that has in common. Each one of them will be good for 100 gigabits per second. That's coming in October. There is approximately 1 petabyte of disk cache available to fire detector. So if we lose both things for some reason, we can cache for a couple of days anyway and still take data. Normal steady state data taking is only 8 gigabits a second, but we'd have to use all 100 gigabits a second to get it all out of the mine. And that takes about 4 hours. Now, when our collaborator realized we could do that at all, well, so the physics here is that when you have a supernova explosion, the neutrinos make it slightly out of the, even though they don't travel quite the speed of light, they make it out of the supernova faster than the light does. So you will get the supernova signal somewhat before the light is. Those who know say it takes about, you got maybe 5 or 10 minutes to let the optical telescopes know. So how do you do this? I mean, this is not easy. You can't get all the data anywhere in 5 minutes. So, and I'll come back to that in a second. So I want to point out the heterogeneous nature of our workflow first before I come back to that. So your CMS or your Atlas, if they didn't have any GPUs, they could still do their whole analysis run. It'll be a little bit slower, but it will still all work. In neutrino physics, not only DUNE, but also the short baseline neutrino things Fermilab, we're using machine learning reconstruction of the track, which is called SPINE, mostly developed by a group at Slack with other collaborators. So in the near detector, you have it's very segmented. Instead of having one big tank of argon, you have a bunch of smaller cubes of liquid argon, so that is a shorter drift time, and it's pixelated, but so you have 3D information both in charge and light. And you have to not only train this on GPUs, you have to run it on GPUs. So we're already using 40,000 GPU node hours at NERSC a year, and that's simulating 1/10 of the data that we think we'll be taking in the course of a normal year. We're talking about having 25 neutrino events in the detector in one spill. This is going to be the hottest neutrino beam that's ever been built. And don't worry too much about the boxes, except that you have some of the things that have to be done on CPU, some that have to be done on GPU, and then you have to go back. So you've got intermediate things. So they have a way to do this now, but it's a bespoke written by a postdoc who was in a hurry. And so we need to make it a more systematic way of flipping back and forth and keeping track of all the intermediate stages and so forth. And it's continued struggle to make it fit in 40 gigs of GPU RAM. If you know Perlmutter, it's got a few that have 80 gigs of RAM, but most of them are 40. And also about half of our code is NVIDIA specific and about half isn't. So how do we get GPUs and CPUs fast? Okay. So we know right now of 3 different places where there's machine learning GPU wanted things in our DUNE workflow right now. One of them is what I just mentioned right now with the track reconstruction of spine. Earlier, they're now also putting it on the signal processing. Signal processing is tricky because there's information both in the parts that go above the line and the parts that go below the line. And then at the end of the event, we have inference as a service. So in that part, you can have many different worker nodes calling out to a shared GPU server running Triton, the Triton server. This requires very close collaboration with leadership class computing facilities. We do not have 40,000 node hours of GPU available at the site of Fermilab. And even if there were any to sell, we wouldn't have a place to put them if we could buy them right now. So we have an active NESAP. program with NERSC at the moment. We have to work with our networking people at ESNet. Yeah, almost done. We'll be fine. We need network routing to be able to send to those facilities depending on which one is up. NERSC is not up all the time. Argon is not all the time, but there's usually are 2 different times that they're up. And then we need, there are new APIs that recently come out in alpha for uniform submission interfaces called the IRI, Integrated Research Infrastructure, where at least one ought to be able to use the same API to support both to NERSC and Argonne and eventually Oak Ridge. So for supernova readout, we also have to get the data with the most pointing info there first. That's towards the front of the event, so that would happen anyway naturally. There's one of my colleagues who wants to actually do his data stream straight out of the, not make it into files first, so he basically just stream raw binary data from there to NERSC. So about 10 years ago, we started looking at fast deployment. How do you get 40,000? You don't actually need 40,000 GPUs. Actually, probably a couple thousand would probably, a couple thousand cores would be enough. But how do you get a lot of up and commission fast? We first started, Ron asked this question of me years ago when we were talking commercial clouds at the time. How do you get 5,000 or 10,000 or 40,000 nodes to all turn on at once and all go off at once? And out of that came the Condor Annex at Condor, and out of that came HepCloud at Fermilab. But we may need a real-time quality of service on the HPC end to be able to do this, and they say they want to work with us on that. Generally, just a word on the overall OSG usage of DUNE. We're dependent on glide WMS factories. We run our own front ends and decision engines, so we don't run in the OS pool. We have our own pool called the global pool. Factory people worked with us very well as we had to flip our remaining resources to site token off. We're dependent on CVMFS, both for code distribution and expanded container distribution. Also for OSDF Pelican, we still end up calling stash cache. It's used for files that are read by a lot of different jobs, but not big enough to store in the regular system that handles data files. And streaming is still an important use case. We're also dependent on the accounting system to get our information to APAL. I did not say earlier, yes, we use the OSG, but probably 2/3 of our DUNE's actual computing sites are in Europe. And we're using the OSG factory to get to them too. So summary, the DUNE CPU and disk storage needs are comparable to clusters that already exist now. GPU acquisition will be a challenge, as will the prompt access to CPU for burst processing. The real challenge is fast movement of events and processing of very big events. And that's coupled with the jobs that are relatively short. The user is doing a perfectly legitimate job. I want to run on 1,000 files. I want to make one histogram of these files. Each one of those is going to take 2 minutes. Which you can do. Catching the output from all that is not so easy. We're currently finding the scaling limits of all our data management services, Rusio, Medicat, FTS. That is made harder by the fact that half of the traffic crawling us at any time is web bots or AI bots. We've had to take mitigations on all of those services to block that. And after we find the data management service limits, we start benchmarking the underlying storage. How many streaming connections can it support? How many total I/O? So we're very thankful to the OSG, its staff, and its member sites who help keep us going. And hopefully be watching the S News Network a few years from now. Hopefully we will have news. Hopefully we'll get it built before the next supernova comes. And thank you for your time.
Ryan, question in the back.
So if I heard right, that it takes about, you're predicting 4 hours to get the entire supernova readout to Fermilab,
Well,
but for optical follow-ups, the opportunity might be 10 minutes.
Right,
Did
yeah.
I hear those right?
yeah, that's our understanding right now. Seeing we don't actually have a fast enough machine there, we haven't actually benchmarked that to prove that, but just based on that, we think so, yeah.
is there opportunity to do a partial follow-up or a rough estimate, or do you need to move all the data to Fermilab to even kind of have an idea of which direction?
No, you
to
shouldn't
take?
have to if you do it right. There's at least one other tactic. There's actually there's actually a published paper of what they think it will take to do it, but once we actually build the system, we have to actually try it and see.
So there's at least some opportunity to
Right.
have the follow-up for all our MMA friends. Rough first,
Yes.
maybe
Um,
from Fermilab, from other places.
The
before
likely
the-
fallback right now is what's called moving what's called the trigger primitives, which are just little text segments themselves and not the whole rest of the event, most of which does not contain anything. That's the likely fallback at the moment.
Very cool. Thank you.
Todd?
One Todd to another Todd. Thanks for the great talk. I do take challenge with slide 3 that you had way back.
Oh, yes, I did make an ask.
Yes,
At
you
one
did.
time, but I
So,
did not come
at
up-
the bottom,
But I did not come up front and complain, oh, this is not working, et cetera, et cetera.
Correct. You did not complain, but you did make an ask
Yes,
for
I did make
the
an ask.
ISI support.
Actually, we made the ask a couple months ago, and we just had time to meet about it now, so yes.
Touche.
Any other questions? All right, I now invite Marone to resume his discussion.
That does not require me up here, I think.
Okay. Thank you for bringing DUNE to our discussion. And if I understand correctly, we have here a multi-messenger challenge of you get the supernova, and what you need is to allocate significant computing power to process it. So the instrument is not moving a telescope to look at it, but making sure that you grab the capacity that you need. Yeah, it's nice, but it's sort of adding another instrument into the multi-messenger, which is the computing capacity. And I feel that part of the challenge moving forward is how do you test that it all works? How do you run dry runs to say, okay, we have a supernova, let's go now.
Especially since all our colleagues in gravity waves and telescopes will also be wanting all the thing at the same time for the very same reason.
Yeah, so we will have a super duper nova. So, yeah, you know, we started with Rubin, and we ended up the day with DUNE, and in the middle we had quite a bit of AI, and I feel that we should find a forum to try and understand how do we turn how do we deploy, manage, and operate inference servers, because I can see quite a bit of challenges of how we allocate them, how do we know who is doing the inference, how do we control the token. By the way, I have no idea what it means to do 1 billion tokens. It's almost like this supernova happened 5 billion years ago. I don't know. I look at my watch and I say, really, that long ago? And so we are really dealing here with numbers. By the way, the weight of the helium is kilotons, that of DUNE. It was KT. What is KT?
Ton is 1,000 kilograms, and one ton is 1,000 kilograms, and then you have 10,000 of them.
I see. Yeah, and I've been all these years complaining about these pictures of LHC detectors. So I wonder how many LHC detectors we can put into this room that you showed us in Dakota.
Let's answer that. I think CMS will fit and Atlas will not, but
Well, CMS is 12 tons. Yeah, and
Yeah, but
yes,
space-wise, can we
Space-wise,
put
it's
both
five-
CMS and Atlas in this room?
Oh, yeah. No, I
Oh,
mean,
yeah.
yeah,
Good.
yeah.
Okay, and there will be still room for,
CMS is 5 stories high,
I,
and
good.
Atlas is probably 2.5 times bigger.
And then we can move in a small supernova into the same room and everything will be. So it's fascinating. It's continuously changing. And I feel we also tried in some of the AI presentation of Eva and the workflows for Dave O'Connor's lab is to think about the single PI environment and how do we get the small things happening, while on the other side we have all these huge efforts coming together. And can we find commonality? Can we find leverage? Can we do better is why we are here. So